We'll go through some review ideas, but then we'll look at a couple problems on the back side here. Okay, density is a measure per given space. Your mass density is a concentration of matter per object. When you talk about a mass density, okay, it's concentration of matter per object. Density is your mass divided by your volume, and mass is equal volume times density. Units for density is kilogram per meter cubed. It's scalar. Density, once again, is just like a mass. Apparent weight is the weight of object in the fluid. Pressure is the magnitude of the fluid. Pressure is the magnitude of a force exerted on a fluid. Once again, you put your hands here and you start squeezing. You start feeling a little bit of pressure there. Okay? Start feeling a little bit of pressure. Okay? Why? Because you're exerting a force on a surface area, so you feel the pressure that's going on there. Force is equal to, or pressure is equal to force divided by area. These are in pascals, newton meters. It's a vector quantity. Force is equal to pass times your air, or your pressure times your area. You have your net upward force is called a buoyant force. Density of water, something you should note here. Density of water is 1,000 kilograms per meter cubed. Okay, the block has a dimension of 2 by 5 or 0.2 times 0.5 times 0.1 meters, and has a density of 1,500 kilograms. Okay, we want to calculate the buoyant force and the apparent weight. We want to calculate the buoyant force and apparent weight. Well, what we talked about yesterday was when you add your weight or add your forces in the y direction, we can calculate a buoyant force here. If we look at this object, we have a force of gravity that is pulling downwards. But what we also have is we have this buoyant force that's pushing it upwards. And how we can calculate that buoyant force, and which is what we talked about yesterday, is density of the fluid times gravity times volume of the object. So we can calculate our buoyant force by density of fluid, gravity, volume of the object. Well, the fluid that we have is water, which density is 1,000 kilograms per meter cubed. We have gravity, which is 9.81 meters per second squared. And then we have the volume of the object. Well, we have to find the volume of this object. Well, we have a block here. And with this block, we have dimensions 0.2, 0.5, and 0.1 meters. So the volume of this object is equal to what, Grayson? .01. Is that what you said? Okay, and that's in meter cubed. So I added my units in here just so we could see what's going on here. The meter cubes are going to cancel out. And my units are going to be left with kilograms, meters per second squared, which is a fig. So we can multiply these all together. To find a buoyant force. And our buoyant force comes up to what, Emberlyn? 98.1. You go with that? Okay, and once again, this is kilograms, meters per second squared, which is a Newton. Okay, so we have, that is our buoyant force. That is our upward push. We want to calculate an apparent weight. Okay, well, how do we calculate an apparent weight? Well, what we need to figure out is I have a force of gravity, I have a buoyant force. I'm pushing up at 98.1 newtons. What is gravity pulling down at? Well, how do we find the force of gravity? Well, that's just our weight. So we have the mass of this object times gravity. Well, what we have to do is calculate what is the mass of this object. Well, we calculate our volume of this object is 0.1 cubic meter, 0.01 cubic meters. How do I find my mass? If I know my volume, what's my mass? Well, I'm given that a density is 1,500 kilograms per meter cubed. Density is mass divided by volume. So if I multiply both sides by volume, mass is equal to your volume times your density. So we can calculate our mass down here as volume times our density. We calculate our volume to be 0.01. Our density is 1,500. And these are all kilograms and meters. So we have a mass of 15 kilograms. So that is our mass. So our force of gravity, we can calculate as mass times our force as acceleration of gravity. So the force of gravity on this object is equal to what? Jacob, what do you get?
Force of gravity, negative 147.15 newtons.
Point what?
15.
So we are pulling downwards at 147.15 newtons. We are pushing upwards at 98.1 newtons. So our apparent weight, what do you think we should do to calculate our apparent weight? What should we do with these, Justin? Divide them? Okay. I got the force of gravity coming downwards. Yeah, force of gravity is coming down at 147.15. I got the buoyant force pushing upwards, so we can add these two together to get an apparent weight. So we have the negative 147.15 plus the 98.1 newtons. So Janae, what did we come up with?
Negative 49.05.
So for me to lift this, the apparent weight of this object is not the actual weight of this object. The actual weight of this object is 147 newtons. Really, I only have to apply a force of 49 newtons to be able to lift it. Okay? Archimedes principle, we talked about Archimedes. Did we talk about Archimedes yet? Did we do Archimedes?
Yeah.
Okay, the volume of the displaced fluid is equivalent to the volume of the object immersed in the fluid, or the fraction of the volume below the surface of the object partially submerged. You want to find the volume of an object? You want to find your volume? Submerge yourself, see how much the water raises. So your volume of your object is equal to the volume of the fluid displaced. If the volume of the object is equal to the volume of the fluid displaced. Okay, let's look what happens here. If we would take the density of the fluid times the volume of the fluid, the density of the fluid times the volume of the fluid, what we get is the mass of the fluid. So when we combine these two together, we get the mass of the fluid. Well, when I multiply the mass of the fluid times gravity, I get the weight of the fluid displaced. So the weight of that fluid displaced is also your buoyant force. So the weight of the fluid that you displace is also equal to your buoyant force. Whatever amount of water that you displace. Densities will determine whether the object will float or sink. If the density of the object is greater than the density of the fluid, the object will sink. Density of air is 1.24 kilograms per meter cubed. Density of water is 1,000 kilograms per meter cubed. Density of ice is 917 kilograms per meter cubed. If you're in the pool and you let out all the air in your lungs, the air bubbles will float. Why? Because the density of the air is less than the density of the water, so they will float. Ice has a density of 9.17. Density of water is 1,000 kilograms per meter cubed. What do ice cubes in a glass of water do? They float. Ice cubes, or not ice cubes, icebergs float. When Lake Harmony freezes in the wintertime, whenever it does, sometimes it doesn't, but you have this ice out on the lake, it stays on top of the water. It does not sink to the bottom of the water. Okay? Because ice is less dense than water. When matters turn from liquid to solid, it will increase in density because you pack it down, because particles and bond closer together, it is more compressed. This is true for everything except water. When water forms into ice, or solid, which is ice, it becomes less dense. So ice will float because we lose density. When water freezes, water molecules form a crystalline structure maintained by hydrogen bonds. Solid water or ice is less dense than liquid water. Ice is less dense than water because the orientation of hydrogen bonds causes molecules to push further apart, which lowers the density. Ice is still ice, it is frozen water. You still have H2O there. It's just frozen H2O. You have hydrogen bombs. You have hydrogen bonds, no matter if you're talking about ice or water. You have hydrogen bonds there. Yeah. But when water molecules freeze into ice, those hydrogen bonds spread things apart rather than compact things out. Everything else, when you go from a liquid to a solid, will compact and become more and more dense, except for ice. Once again, icebergs, they float. They cause problems for the Titanic. A spherical helium-filled balloon with a radius of 15 centimeters floats upwards in the air. Helium floats. Makes our voice very funny. But is held in place by a thread attached to a spring, which stretches until the balloon rises no further. The density of helium is 0.164 kilograms meter cubed. Density of air 1.24 kilogram meter cube. How large is the force exerted on the spring? Assume the weight of the balloon material, the weight of the balloon and string is negligible. So you have this balloon range of 15 centimeters, floats upwards, and this is full of helium. And it's floating upwards. Fluids are things that flow. Okay? Fluids can be a liquid or a gas. You have air that is here. That is a fluid. The balloon is floating in the fluid of air. The air, the reason why it's floating in air is because air is providing a buoyant force pushing upwards. You are also in air. If you would stand on your chair and jump, you are submersing yourself in the fluid of air. But your force of gravity is greater than the buoyant force. The air will provide a buoyant force towards you to try to lift you up, to try to keep you in the air, just like a helium balloon. And you could be in the Macy's Day Parade Day, floating on the strings, going down the street. Okay? So the air, what we live in here, is providing a buoyant force. This object right here, okay, there is a buoyant force that's pushing up on this. But the force of gravity, see the sun's out. So you say there's a chance. Told ya.
It's still raining.
But the sun's out. Look at that.
It'll be fine.
You have the force of gravity pulling downwards. You have the buoyant force pushing upwards. For helium balloons, the buoyant force is greater than the force of gravity on that balloon. Okay? For you and for this, it's not. Most of the things that we have will fall to the ground because the buoyant force is not strong enough and it won't overcome the force of gravity. But there is a buoyant force existing for every time that you jump, every time that you're moving or jumping off something, there's a buoyant force pushing up, just like in water. If you jump in a pool, you don't sink to the bottom, hopefully. Okay? You will bounce upwards, it will support you, and it will allow you to come upwards because your force of gravity is not stronger than the buoyant force. And the reason why is air is not very dense. Water is a lot more dense. So what we have here is we have a force of gravity that's pulling downwards, but then again we have this buoyant force pushing upwards. Well, we need to calculate the buoyant force. And how we calculate the buoyant force is density of the fluid times our gravity times the volume of this object. So what we need to do is we need to find the volume of the object. Well, how do we find the volume of a sphere? How do we find the volume of a sphere? Oh, Scout students. Related rates.
Oh, is it pi r squared? I mean, not squared,
That's-
cubed.
That's close.
4/3.
There you go.
Wow, you could. Sure. Yeah, I know. You're right.
So the volume of the object or the sphere is 4/3 pi r cubed. Now what we have to make sure of though is we have densities that are in meters cubed and we have a radius that is centimeters. So we need to convert centimeters into meters by dividing by 100. So we have 4/3 pi times 0.15 cubed. And I see it. I see all the evaporation going on out there right now. It's like I go outside, my hair would frizz up or I'd lose my curl. Because all the humidity out there just curl away, it go away. And all my hair, it flatten out. Hate it when that happens. All right, so we get the volume of the object. What's the volume of our object here? 4/3 pi r cubed. Seth, what do you get?
0.014.
0.014 meters cubed. We good with that? 0.014. 4 times pi times 0.15 cubed divided by 3. We all good with that number? What are you getting over here? Peanut gallery.
Yeah, that's about right. I just didn't multiply by 5.
All right, you left in turn to 5. That's fine. So to find our buoyant force, we have the density of the fluid. Well, the density of air is 1.24. Times gravity, 9.81 meters per second squared, times our volume of the object, 0.014 meters cubed. Our buoyant force we come up with is what? Kate, what do you get?
0.17.
0.17? 0.17 newtons? Yes, no, maybe so? All right. So that is our buoyant force. But what we have, let's see, what is exerted on the force of the spring? So we wanted to figure out, well, what's this exerted force on the spring here? We have a scale down here. Well, we have the buoyant force pushing upwards, but we still have the force of gravity. That's pulling downwards. Well, what we need to figure out still is the force of gravity. That force of gravity is weight, which is mass of the object times gravity. Well, we need to find the mass of the object. Well, the volume of the object is 0.014. We have the density of helium is 0.164 kilograms per meter cubed. So to find our mass, once again, mass is equal to volume times density. So we know our volume, our density, 0.164. So that will give us the mass of our object, and then we can multiply that by gravity to find the weight of the object. Once again, this just gives us our mass. We have to multiply by 9.81 then. Janae, what do you get for the mass of the object?
0.0023.
Then we can multiply by 9.81 to find our weight. Our weight comes down to what now?
1023.
0.0023 times 9.81.
1023.
0.023. So that is my force of gravity going downwards. My force of buoyant going up, 0.117. Once again, we can subtract those two to find what is my net force going upwards. What do you get? What do you get?
0.147.
If you did not have a string there, you would still have this force, sum of forces going upwards. You'd have a force net to be this. So if you wanted to, that force net is equal to mass times acceleration. You could also calculate your acceleration. How fast is it going upwards? It will continue to accelerate. going upwards because you have a force net. So you can go in a vertical sense in regards to force net equals mass times acceleration. I'm telling you there's a chance. Yeah. Say yes. Say there's a chance. But there's still a chance. We will stop there today. We will go over just the one problem tomorrow at the bottom. That will be it. Because I don't want to waste the gas mileage of those two coming in.
That would be nice.